So motion graphs then, often the speed time graphs are taught and then distance time graphs are taught, and maybe the other way around, but it's good to teach them at the same time as well. These questions here are quite difficult. We're having to calculate the area, so we'll look at why that is in a moment. But let's start at the distance. In fact, no, let's just look at these examples here. This is a speed time graph, and over on the right, this is a distance time graph. We've got the blue lines in both cases are high gradient, and the pink lines are low gradient. Now let's compare what each one would happen at this dotted line. They've both reached the same speed. No, sorry, they both reached different speed at the same time. But we can say the blue line has reached a higher speed in the same amount of time. So this means it has a higher acceleration. Now, when you learn a bit more about acceleration, you'll learn that acceleration is the rate of change of velocity, not the rate of change of speed. But most of the time, it's kind of the same thing. Not all the time, but for most of the time. So if the speed is increasing, we know from day-to-day experience, if we say that speed is increasing, then it's accelerating. Nothing wrong with that. But it's actually true to say that sometimes you can actually have the speed staying the same, but it still accelerates. But we'll do that in another lesson. So the blue line, so basically the high gradient, so we can write down here, well, in fact, we've written it over here, look. So the gradient of a distance time graph is the speed. Okay, so let's color in those two green, because I've got the axes there in green. And then if we look at the gradient of a distance time graph we're talking about the same period of time, same point in time. The pink line has reached a much lower distance than the blue line, and so what we can say is, let's get a nice blue, no, we want an orange one this time. Yeah, so we can say the blue line has reached a higher, okay, let's try that again, a higher distance in the same period of time. So it must be traveling at a higher speed. Okay, so there we go. If it's traveling at a higher speed, I just realized I colored that in wrong. No. Okay, so that was the one that we just did. Sorry about that. That was the one that we just did. That's orange. So the previous one, it had a higher acceleration. So this is the one that I should have colored in green. Oh, come on. Okay, so let's color that in green. Okay. Right. What about the area under the graph? As I've said here, is the distance. Now, it's a bit complicated to understand why that's the distance. So we'll start off by just saying, well, it is just the distance. The area underneath a velocity time graph or a distance time graph is the distance, or we can say the displacement, but for now we'll just say the distance. The area underneath a distance time graph doesn't tell you anything. So let's try to understand why the area underneath a speed time graph will give you the distance. If we look at this one here, this is where we calculated the area. So I'm just going to get rid of all the working out that all this stuff here, and I'm going to try to understand why is it that the area underneath the graph represented that. Let's see, okay, get rid of that. That's their dotted lines. Well, let's just look at this bit here when they're moving at, this is a velocity time graph, they're moving at a constant velocity. Between the time 3 seconds and 7 seconds, they moved at a constant velocity, 5 meters per second. So for that period of time, we can say that t was equal to 4 seconds and that the velocity was equal to 5 meters per second. Well, we know that the velocity is equal to, if for constant velocity situations, is equal to distance divided by time. So this is a constant velocity situation, so rearranging that, we can say that distance is equal to velocity times time. Well, the velocity of is actually just the height of this rectangle, and the time is the width of this rectangle. So here we can see that velocity times time is the same as the area. And how does that work when the velocity is changing? Well, basically what you do is you imagine, rather than it's changing gradually, but we can imagine it changing in increments. So we could imagine, we could make this into a staircase, perhaps like this. So let's just color it in or make it transparent so we can still see the line underneath. Oh, okay, I wondered why that wasn't working. It all happened at once. So it would be something like this, right? Let's do one more. That worked out pretty nicely. So if we imagine that instead of it going gradually up in a diagonal line, it was constant, and then suddenly it was this new constant speed, and then it was this new constant speed, and then it was this new constant speed, and then it was this new constant speed. I'm just going to stretch it so as it matches up. Yeah. Well, if that was the case, then we could say for each one of these rectangles, we can treat it the same as the large rectangle. And so we could say that the distance, so this would be, the height of this rectangle would be the velocity for this period of time, the height of this rectangle would be the velocity for this period of time, and so on and so forth for each rectangle. So we could say that, and then the width of the rectangle would be the time. And so once again, the area of each rectangle would give you the distance traveled during that period of time. Now, obviously, we know that the velocity didn't change as a staircase like that. It didn't go constant, suddenly a new constant, suddenly a new constant, and so on. But it changed gradually. Well, what we could do then is we could imagine taking these rectangles and shrinking them down, and increasing the number of them, right? So we could say that's the. I'm not going to get it quite right now, but actually, I'm going to pause the video just for a moment and show you a simulation that does this much better than what I'm attempting. So here we go. This is a perfect example of what I've just done. We've got the straight line, which looks like I can move it as well. Or I can even, is that curving it? Yeah, it is. Cool. So it shows you that it would work as a curve. It doesn't matter what shape you do. You could do a curved line, or you can, it doesn't really matter. In fact, we can move these as well. That's quite cool. So the point is that I can divide this, and I could say that, let's imagine, rather than go up in a curve, it's just a constant velocity, then a new constant velocity, then a new constant velocity, and so on. The area underneath each one of these would be the equivalent of the distance traveled for that constant velocity, as I showed earlier on. But the smaller I make these rectangles, the more accurate it is to be the genuine area underneath the actual curve. Okay, until eventually you make it so small that the area is essentially spot on, right? So the area, because what we're saying is that the rectangles are infinitesimally small, or infinitely small. They're so small that they have a width of 0, which doesn't really make much sense. But this is kind of like this is like an introduction to A-level maths here, but just as a basic explanation of why the area underneath a speed-time graph gives you the distance is because imagine breaking it into smaller and smaller rectangles, and each rectangle we can imagine being a constant speed. So yeah, hope that makes sense. And I'll just stop the video there.